Alright, so let's consider this problem here. The area inside one petal of r equals sine of 5 theta. Sine of 5 theta. So we can go ahead and take a look at the graph here of r equals 5. Not 5, it's just 5. So sine of 5 theta. So zooming in, you can see, first of all, this completes a full circuit by the time we reach pi. So let me zoom in here a little bit. And so we just need to pick one of these petals, but the problem is, where does it start? Well, let's put my slider on here, my parameter A, and let's start drawing it. Now again, A is based on pi over 12. So you can see right around here, it's finished, its first petal. But again, these are not coming in smoothly like they were before. So we need to know, let's say with this first petal, we can see it's starting at 0, but when does it finish up? When does it finish up? So that's a question we have to ask. When does it finish up? Because that'll be our second limit. So with that in mind, we know that this rose petal finishes between places where our radial function was 0. So if we just look to see when is our radial function 0, right? So when is our radial function sine 5 theta equals 0? That would happen at 5 theta equals the places that make sine 0, which is 0, pi, 2 pi, and so on. So that would make theta be 0, pi over 5, 2 pi over 5, and so on. But the only ones we need here are the first two. So that first value is happening at pi over 5. At pi over 5. So to get the full area, it would be the integral from 0 to pi over 5. And so we set that up. Integral 0 to pi over 5 of 1/2 my function squared. Should be sine squared of 5 theta d theta. To do that, we need to convert it over to cosine. Remember, sine squared of something is 1 minus cosine of twice the angle over 2. That means I'm going to need a 1/2 involved. So I'm going to put that 1/2 with the other 1/2 to form a 1/4 on the outside. 0 to pi over 5 of 1 minus the cosine of twice the angle. The angle was 5 theta. So that will be 10 theta d theta. All right, and now we're ready to work the integral out. So for that, we'll have to do a substitution for the cosine. So u equals 10 theta. du equals 10 d theta. So I'm going to have to put a 10 with the d theta for that one to carry it through. So on the outside, I'd have to divide. So putting all that together here, integral of 1 is just theta. So we'll have a 1/4 theta. Minus integral of cosine will be sine. So that will be a sine of 10 theta. And I'll have the 1/4, but I needed to account for the 10, so I put a 10 with the d theta. So the substitution can carry through, so I'd have to divide by it on the outside. So that's actually going to be minus 1/40th sine of 10 theta. And then we evaluate that between 0 and pi over 5. You know, we work that out. And what we're going to find out is we put pi over 5 in. That's going to be pi over 20. We put pi over 5 in. We multiply by 10. 10 times pi over 5 is going to be 2 pi. Sine of 2 pi is 0. And of course, when we plug the zeros in, they're all zeros as well. So turns out the area of the single loop of the sine of 5 theta is pi over 20. Pi over 20 is the area of that single loop of the sine of 5 theta. Okay, so here again, what we had to do is just understand a little bit about how this graph was coming about, because I wasn't able to just count up exactly, right, as I was coming through. You know, it started at 0, that loop, but it might have been a little hard to see when it finished. So what I did is I realized it's going to finish when it hits 0. So I know between my first two 0 values, that's going to be my first loop. Between the next two 0 values, that would be my next loop. Between the next two would be my next loop, and so on all the way through. Okay, so from that I was able to set up my limits. Use this common substitution here. Sine squared is 1 minus cosine of twice the angle over 2. Remember, if it was cosine squared, it'd be 1 plus cosine of twice the angle over 2. Okay, and then we were able to work out our area.